Good morning, everybody. We are very happy here to welcome the laureates, the two laureates of the Chemistry Wolf Prize for 2021, Professor Leiserowitz and Professor Meir Lahav of the Weizmann Institute. And before asking you the first question, I want just to ask you a word about your co-workers. Of course, you represent many other people who were part of your discoveries, and maybe you want to say a few words about those people who were part of this discovery, although you have been recognized as a leading figures of this discovery. So perhaps you can say a few words about these people.
So I would like to mention some people that participated in the discovery. Among them, Dr. Leah Dadi, who is now professor in chemistry. Dr. Ziva Berkovich, the late Dr. Ziva Berkovich. There is Isabella Weisbuch, Dr. Isabella Weisbuch. Edna Shavit, who worked with us, a technician, but she did a lot of the crystal growing part, which was very important. And Dr. Ronit Popovich. I think that these are the main people that work from outside. What about you?
Well, I think afterwards when we worked on thin crystalline films, I think we made a connection with Professor Jens Nielsen from Denmark, University of Copenhagen, and he was a pioneer in the study of surfaces. This was both the crystalline surface at the crystal surface and at liquid surface, and I think we owe him quite a lot for our understanding eventually of the X-ray scattering processes that you find in crystals. I think he was the dominant person that we would like to thank. Jens Nielsen and his postdoc, who was Christian Kerr, who worked together with him. They had developed this crystallography at liquid surfaces. From the technical viewpoint, it was extremely important.
Okay. There are several questions that I'd like to ask you, and I think the audience will be very much interested to listen to your stories. We are all happy with the Wolf Prize. Congratulations. For a long time, we didn't have laureates from Israel, which is a happy moment for all of us. One reason I want to ask you the following question is related to the fact, or to our mission, to educate the young generation. And in my view, the reason we give prizes, the Wolf and other prizes, is because we want to define heroes and role models for the young generation to follow, and to attract the young generation to science and engineering. So in order to do so, it's very important to understand where it all started, and how did you personally been attracted to science. And for example, I'll give you an example. Danny Shechman told us some time ago that he understood that he's going to choose science for his career when he was in the kindergarten, when he received a magnifying glass for his birthday. I don't know if it was 4 or 5, but using this magnifying glass and starting chasing all kind of beetles and small things, the rest is history. So this question is for you. How early in your childhood did you understand that you're going to become a scientist? In the childhood, or probably later in the elementary school and high school. So how did it start?
Well, I was brought up in Johannesburg. My family had one foot in Joburg and one foot in Cape Town. And of course, all that I did was I roamed the streets of Johannesburg with an old friend of mine. But I knew what I didn't want. I didn't want to become an accountant. I didn't want to work in an office. And I think, but I had no idea that I would get involved in science. In fact, nobody ever spoke about science in my family. Johannesburg was a gold mining town, and so mining engineering, was very important. I had absolutely, and in fact, when I went to school, I was interested. I liked science. I mean, I liked mathematics and physics because I understood it. I mean, you know, the other topics, but that was basically, but only when I went and studied at university. I studied engineering, electrical engineering, because it is a way of earning money. But I couldn't get work as an electrical engineer. I worked for the South African Railways for a few months, and that was a dead end. It was an absolute dead end. I then left the railways, and I started looking for work. But you know, you have to know how to dress. You have to know what kind of work you want to do. And this went on for a long time. And eventually, but I went up Table Mountain all the time because I was sick and tired of looking for work. And then I bought two books. I bought a book called The Crystalline State by Bragg and Bragg. And I bought another book called The Optical Properties of X-rays, because I'd studied electrical engineering in Cape Town. And that was basically, my mother was a designer and maker of dresses. Mm-hmm. And so our house was always full of patterns, fabric.
Yeah.
And it was the patterns in the book by Bragg and Bragg. I didn't understand space groups and that, but I liked the patterns of crystals, the way the molecules, and that is what led me into science, basically.
Wow. Amazing.
Yeah.
So self approach, not by teacher, not by anybody from outside, but from reading books.
Yes, but one book I did read that amazed me, and that was a book called, it was by a naturalist. His name was Eugene Meir. He was a South African. He wrote a book in Afrikaans about the soul of the white ant, because he asked himself, how is it that the white ant in South Africa, they build these beautiful structures? The ant has no memory and therefore cannot think ahead. So how he wrote this book, and he observed for 3 years, and when he wrote that book, I thought, my God, that is what I would love to do. And that really book inspired me. It was during that time I was on Table Mountain. I read that book.
Wow. Okay. So what's your story?
My story is very, very different. I was born in Bulgaria, in Sofia, 1936. The war started in 1939. And in 1942, since the Bulgarians were together with the Germans, we were forced to leave our homes in 1943 from Sofia. We left our home with a single suitcase. My father was working at that time in a working camp. So my mother with my sister, we went to the synagogue of Sofia, and from the synagogue of Sofia they took us to some trains and then pick us to a small city near the Danube on the way to Auschwitz. And then we stay for a year and a half, under very difficult conditions, waiting every evening to be taken from this city to Auschwitz. But we were lucky in 1944 when the Russians came and they could save us. So we were able to return back to Sofia. Now, At that time, I used to learn in a French school, to learn French, to learn some Bulgarian, but no. And then in 1948, establishment of the country. First of all, my sister was taken to Cyprus and to Israel, and it was very clear for our family that we are going to leave Bulgaria for Israel. And I came to Israel at the age of 12-13, without knowing a single letter in Hebrew, without knowing anything in English, because the first thing that I knew was Bulgarian and French. And then you have to start for the very, very beginning, right? To start to learn Hebrew and English. So the first month we spent in Beit Olim in Pardes Chana, and then we moved to Ramla. And two families, one in a garage, and they have to clean the garage, and there were two families in one room. This was for some third time. But afterwards, we decided to move to Haifa because my mother had an aunt in Haifa, and we went to Haifa, and I sat in a Hebrew school, in a 6th class of an Hebrew school, without knowing a single letter in Hebrew, right? I could follow somewhat the courses in mathematics, in calculus, but not could understand anything. Well, we were lucky that a few months later, we moved to Kfar Atta, there was a new building of a new of Bulgarians, let's say, we call it Shikuna Bulgarin, the problem. And then went to school there. And this is very right, because it was a small class. There were only 10 people in the class. So the teacher took care of us. They could take care of us because there were a few newcomers in the school. And it was I think we were able in 2 years to learn some Hebrew and to learn some English. For the high school, there was no high school in Kfar Atta. The high school was in Kiryat Chaim. So there was no any other transportation than except a bicycle. So every morning, I have to bike from Kfar Atta to Kiryat Chaim. It took about 3/4 of an hour in one way. And this also in the winter. You have to do that. And I enjoyed very much the high school. It was here that I was able now, they start teaching some new fields like chemistry, like physics, like mathematics. And this I could understand at a certain point. It was not like Hebrew and all. And here in particular, I enjoyed the lessons in chemistry. The reason was that I had a teacher in chemistry. He was also a newcomer first of all, from France. And he had a very unique method to teach the field. He was telling something in one of the lessons, but after that he was sending us to the library to see all kind of what we can learn from the topic that he was teaching us. And the next hour, he used to examine not what he have taught, but what we learned in the library.
At the library in Hebrew?
In Hebrew, of course. And I enjoyed that very much. I enjoyed this technique to go to the library and to start searching for all kind of information and this was very exciting. And this was different from the let's say, of teacher in physics or in mathematics. They were very good teachers, but they used to come and to bring us the information. And if you learn it by heart, you could be very successful in the next hour, right? But in this case, in the next hour, you have to see what he's going to ask you and whether you succeed to find that in what is written in the literature. And I think this was something which was very inspiring, and my feeling was that this was the reason. I think this this teacher that knew how to excite us, and the problem led me to go to chemistry. I remember once, when I was studying in the university, he came to visit, and I came out from the building of another building another building, not the chemistry building, of law, the building of law, and he looked at me and said, "Ha ha, you went to law, not to chemistry." I told him, no, this last lecture was in the building of law, not in chemistry. I'm doing the chemistry. And the next story was that now that we got this prize, happened something very exciting. I told this to my daughters, that I was very inspired by this particular teacher. And they asked me, maybe we can really detect the family or detect something about this particular teacher. And they went to the Facebook, and they found actually the daughter of my teacher, and they found his grandson. Now, his grandson was a musician, a composer.
Okay.
And they show us a kind of a music that he composed on the poems that were written by our teacher. Two very important points. So I called his daughter, and now we have a contact. We have established a kind of a contact between the people, and it was a very nice opportunity for me to try to thank the family about the inspiration that I received from their.
What was
father.
the name of the teacher?
Ehud Keinan. He wrote 2 books in teaching chemistry. He was also teaching in the Technion. Newcomers that were coming to the Technion, he used to teach together with Michael Case. They were 2 very interactive. But I think this was, a very inspiring point to this prize, that I was able to make a contact with my teacher who inspired me to move into this field.
Okay. So that's an attraction to science. I understand what attracted Les to crystals. How did you come to the world of crystals?
This led much later. During my science in the university, I learned chemistry in the university. At that time, there was a direct route to master's degree. So I did my master in chemistry using ammonia. You know that. Reactions in liquid ammonia, right?
Okay.
And I disliked it. And at this time, I had the opportunity to read some papers of a French scientist, Adolphe Shapiro, of polymerization in the solid state. And I was very impressed by the fact that in the solid, you can perform chemical reactions, and you can monitor the reaction by applying different diffraction techniques. So I thought that it is much more simple and deep to try to understand chemical reaction by performing them in the solid state. And this was the way that I decided to move to the Weizmann Institute with Gerhard Schmidt in this department to start doing chemical reactions in the solid phase.
Okay, and the rest is history. Yeah. Now, what is really fascinating with your work is the role played by the state of Israel in this story. Here's a guy from South Africa. Here's another one from Bulgaria. There's no chance for both of you to get together under any circumstances, except this crazy situation where both of you came over to Israel and found yourself and created history. My question now is, how did it happen? How did you meet for the first time? And how did you know, and when did you know that you are going to have a lifetime work together, an achievement?
Well, I don't think we knew that, but when I came to Israel, when I came to the Weizmann, so I came here, I had an inkling of knowledge of crystallography. I knew very little chemistry. In fact, it was at the University of Cape Town that a PhD student there started teaching me chemistry. And so but I knew a little crystallography. So when I came to the Weizmann, I began to, I applied myself in the field of crystallography, which at that time was a very painful subject because solving a crystal structure was really hard work. And I had developed this knowledge of crystallography. Meir came to the institute, I think, 2 years after I did. I think it was in 1960.
62, December
yes,
62.
About something like that. And I think it was this knowledge that I had somewhat this knowledge of, in fact, we complemented each other because Schmidt was both a crystallographer and he was both a chemist, right? He was the head of our department. But it took a long time for us, I think, to start working together. I think after Meir, after you returned from your postdoc,
Yeah.
then we started speaking to each other about it. Meir and I then started discussing problems in chemistry, and from these discussions, everything began. But what do you have to say about the Meir? I thought I knew one thing, that when we worked together, we never argued about students. We never argued about funding. And we never argued about giving credit.
This was the most important part.
But we
There's
didn't.
a problem, because the point was the same: never credits, never work fighting for credit.
We never discussed it.
Never discussed that. Right? Who is going to be first? Who is going to be
No,
far?
never.
That's the
And even
problem.
writing papers. It was
no.
never discussed. Somehow it always worked out without any rancor, without any discussion. And I think that was, in a way, the basis. But of course, we argued all the time about science. That was, I think, that was legitimate and part of the problem. But we never had any arguments about matters that was not related to science. Never. About money, never. About students, what the student was going to do, whether he was going to go a little bit on my side, a little bit. But it always worked out, and it worked out for 20 years. Only afterwards I began to realize what a rare situation it was.
So it was 1962 when you came to the.
He came
I
in
came at the end
59.
of 59.
Okay, and then you came from postdoc 2 years later.
No, I came to do my PhD in 1962.
Okay,
No problem.
okay, and then you met.
Oh, we met? Yeah, then we met. I
Okay.
remember.
Uh,
So the question was why I select to work in crystals. Already I told you
Yeah,
I
yeah.
like to do some chemical reactions. But at that time, even in the courses of organic chemistry, I remember when they used to describe a certain compound, they said this was done by X-ray. Because at the time, X-ray was such an esoteric topic.
uh-huh.
And then in the course of physics, there was a guy that the professor taught us about diffraction, about break and break.
Yeah.
So this was a kind of a curiosity to learn something and to understand how crystals are, how the structure of crystals are solved. Okay, so this combination was very important. But I think I want to add one point to Leslie. I mean, what was very inspiring at the time, I must admit, was the department. There was a very unique department at the Weizmann Institute. It was in the Ziskin building in mathematics, where it's mathematics today. There were 4 rooms. The entire department was with 4 rooms. But there was the following. There were a few crystallographers
In one room.
in one room. There was photochemist. Mendel Cohen was a photochemist. There was biology, where it was Wolfie Trapp and Ada Yonat. There was this particular part. And there was organic chemistry, and Schmidt wanted to build something new in organic chemistry. And I think I replaced another PhD student in organic chemistry. And I feel that this was very, very impressive. And it was very different from what I did in Jerusalem. Because here you have a multidisciplinary project. And what you want in this multidisciplinary project, you know that you can do your chemist, you can contribute to the problem, but you have to interact and you have to collaborate with others. So even the structures that I use for my PhD were done by a student that Leslie actually, there was 2 Greek guys that were doing the structures of the compound that I was using for my chemical reactions. Okay. And this time, it started this connection. And after when Schmidt died in 1971, and I returned back from the United States for my postdoctoral studies, we decided that we can continue our collaboration. And the moment that we found some findings, and it was clear that such findings cannot be solved by chemistry alone, then we have to find some way to try to interact and to collaborate. And I think that this was a very, very fruitful collaboration.
Well, I think, as Meir mentioned, we were very lucky at the beginning that we had such a department. There was Fred Hirschfeld, and he was, I thought, a brilliant physicist.
Mathematician.
He was actually a mathematician. Mm-hmm. He invented mathematics.
Okay.
He was a superb computer programmer. Remember, at the beginning of those days, we worked with the Weizmann. The Weizmann was a copy of the Maniac. It was a 4K machine with a random access memory. That was all. Paper tape.
Okay.
And so there was also Philip Copeland's, who became very well known in the States, and then, as Meir said, there was this combination. It was also, there was an intellectual environment that was sort of brought about by Schmidt, and this intellectual environment, where one probed the question deeply. This, I think, was passed over to us. I think there was no doubt about it.
What was exciting?
Yes.
What was exciting? The tea time.
Uh-huh.
When you're going to tea time, you have everyone sitting and everyone expressing his own project and his own problem, and you could get a lot of input from a completely different, different field or subfield in science. And this was, I think, really inspiring. Uh-huh. And I feel that this was very, very important for our, and this was also the discovery. How we found this discovery, there was a beautiful story about that. We were growing crystals. So the problem is that, like a physicist Vazel, they tried to solve this problem before us, and he was wrong before that. But the point was that we started growing this crystal, and we had some questions in crystallography, and we came to Leslie, and I had a problem and say, Leslie, we know how to solve a problem in crystallography that you cannot solve. How you determine the two enantiotopic faces of a centrosymmetric crystal. And then he look at us and say, what are you talking about? I know that. We can solve that. Okay? And then when he said he solved it, it was a very important point. We look at each other and said, now we can solve the problem. After this combined information of how you grow the crystal and a fact which was not very well known, because Arrigoni, when he heard about that, he didn't believe on that, and anytime when he was traveling around the world, he was asking all kind of crystallographers whether asking that question, and very few of them could reply to this particular question, but Leslie knew about it. And by combining his information with our information, this led to the solution of this problem.
So that was the eureka moment. That was 1982 or 83? When was it?
I remember.
Something like that.
Yeah. Yeah, this was something before we published the papers in 82, so it must be 98 or something like that. Nature. But this was a very inspiring character. So we went to the literature, okay, and to search for the particular crystals where it can really perform this experiment, we take the serine with threonine. This was the first example, which was very nice. I think this is a very nice paper in this part. And then after that, we consider that with glycine we can solve the structures, the absolute configuration of all the amino acids. But if you want to see what was our combination was, that you come with some idea of something that you don't have the background, you don't have the background in crystallography. But then if you take some result that appears in the chemical laboratory, and you take the information of crystallography, which is very different, and combine the two informations, you can come with some new thing that other people would not have done because they didn't have this kind of combination.
You see, there was something else. It was also the link to morphology of the crystal. You know, all this work, it was the link between chirality and
molecular chirality,
morphology, right?
And morphology, right.
Now, what was interesting was I had all the tools of morphology in my
Available.
pocket. Because during my PhD,
Yeah.
I was asked to solve a problem. I had to take care of what is called absorption of the X-rays in crystals.
Uh-huh.
At that time, I was trying to find half a hydrogen. I think it was a tenth of a hydrogen atom. It was in 1962, 63. It was a hopeless problem that Schmidt gave me.
No, but later on you find another system where you solve that problem.
Yes, years
Because
later.
the techniques become the techniques
Yes,
become
later.
much more available. They were not available in the early days. So in the later stage, they available, and it was possible to do that, to determine the structure of a single percentage of an hydrogen.
Yes, that was the problem that was given to me. And so I got fed up, and I wrote a program, a computer program. It took me a year and a half of how do you account for X-ray absorption in crystals. That means you have to be able to measure the faces of a crystal, and you have to be able to fill that crystal with all sorts of points. And that eventually I filled the crystal with molecules. And then I understood very well the surface structure of these crystals, but I didn't know what to do with it.
I was working with Leah because she was my PhD student at
Yeah.
that time. And then we were working on the problem of origin of chirality.
Yeah.
And we were using crystals for that purpose. But during these studies, we encountered an effect that it was possible to manipulate the morphology of crystals in a given form, right? And Leslie, you knew, because of the problem of morphology, by combining now these two subfields,
Okay.
it was possible to come with these interesting results.
But this is more than that. It's in my view, because I know you for so many years, and the interaction is really unusual. You mentioned you never worried about credit and worried the name, who is first, who is second. Tommy Bazov told me a story.
Now you get an email from him.
couple of days ago, he told me that about the way he went for a postdoc with Jeremy Knowles. Originally, he got a negative response from Jeremy because there was no place for no vacancy, and he was very sad because this is what he wanted. And it was 12 midnight when he finished working in the lab with Moody Sheves, and he went out from the fence of the Weizmann Institute back to his home, and he was very sad. And when he went out to the Hanassi Harishon Street, he saw two people walking back and forth. He told me, Meir and Les, always at night they work. This is how they can. So it was nothing unusual. 12 midnight, they kept working and talking. This is what they've done all the night. So, and that was also my impression.
I'll tell you a story. We were Monday in the car of Vlado Prelog, a Nobel laureate,
Yeah.
and we were arguing. And Vlado asked, I cannot understand how you two people can work together.
Okay. Yeah. Okay. So that's a power of complementarity. Okay.
Yes, I mean, well, there are some points on which we agreed that we would disagree. I remember it was in connection with the induced nucleation of ice using monolayers, the so-called odd-even effect of number of carbons in the chain. I think we discussed it for more than 15 years. We never, I think, came.
And still, we don't agree.
Well, I think I have eventually a model, because Meir worked eventually on the induced nucleation of ice using it was
Pyroelectric
the
crystals.
pyroelectric effect, and I have a model that he rejected. I think we met in March or April, but I think I have, in fact, based on that model, I think I understand now the effect of the odd-even effect in ice nucleation. But by and large, we always came to a conclusion. Because after years, after months of discussion, we would always zoom in onto a conclusion, and that conclusion was generally correct as far as, but the argument was always scientific. It never,
Nothing
became
personal. Yeah.
Never. I don't ever remember that.
Yeah, that's true.
It was never personal, and it's not as if you argue today and tomorrow somebody would be angry. We would come to, it would go on until we realized we could come to an understanding of what was going on. Nothing
see,
that
you
was
can
absolutely
imagine-
correct.
You imagine what was the challenge to try to convince each other? I remember coming for a problem in the morning.
Yeah.
Leslie, I have a suggestion. No, you're wrong. And then you have to take time, and this raises a lot of discussions and conclusions, and finally we came to something which is which is acceptable.
I think
That
there
is
was
about-
also something else with the papers that we wrote. You see, Meir, I think, is organized in his head, but not on his table, not on table. I think I'm a little the reverse. And when it came to writing, Meir always knew what to write, but he didn't. It was always difficult for him to write in English. I always had problems in writing, even English. And so always when we wrote, it was a slow process. And we always chose the simplest words and without jargon. And so when I looked at our papers afterwards, somebody wrote and said, "Listen, your papers are so simple." I said, "Well, that is a compliment."
Okay.
No, but you see, his advantage. He knows English, and my English. I started learning English at the age of 15. So this was a big difference. And I had a big advantage about that, because the moment it comes to write in English or something like the problem, of course he has the advantage that he cannot argue against that.
So that's wonderful collaboration. I have another question. How important in your lifetime achievement, etc., was the environment? The fact that you operated at the Weizmann Institute, and this is basic science. We're not talking about any application here. You didn't think of any application, and this is basic science, and this is development of basic science. And this is also related, if I look, for example, at the achievement of Danny Shechtman, it's also related to structure, to crystallography, and probably the fact that it's another Israeli institute where everybody is free to do whatever they want, and this is not trivial. It's not. You cannot find it in many other places in the world. So, how important was this component of absolute freedom you enjoyed and others to achieve?
We used to have some applications. For example, we have a number of patents about separation of enantiomers, actually, and we had a connection with companies that supported our approach, okay? So the point was that we were looking on the basic science, but also our eyes were open for possible applications. Like the problem that we are working together now today about ice nucleation. We are seeing whether we can prepare new materials for cloud seeding. That's something which is so. But indeed, I think the most important part was the basic science. I think this what in the Weizmann we were given the facilities, and I think to try to concentrate on basic science. So this was enjoyable. I think enjoyable. Period, enjoyable technique to work on basic science and to work on what you are interested in, and to expect that something important will come out of that.
It was a spin-off,
but
you can never predict the spin-off, and so and I think it was in the year 2003 or 4 when Meir and I separated, basically because we were retired. There was a question of money and all sorts of factors. So I entered the field of malaria. It is true that in all the aspects that I worked on, there was the definite connection between what Meir and I had done previously. It was the effect of tailor-made additives on crystallization, That is basically the effect of quinine on the growth of the malaria pigment crystal. There was the effect of the nucleation of these crystals of the hemazone of the malaria pigment by the membrane, biological membrane inside the infected red blood cell. That was a clear connection to what we did when we used monolayers of antiphilic monolayers to induce nucleation at the air-water interface. And then there was a third effect, and that was that we worked for many years, right, on how do you determine the nucleation of a crystal using tailor-made additives. And so there was an absolute connection, but these connections can never be predicted. So the fact that we worked on problems that we thought of and we were not constrained really turned out in many cases to be very fruitful.
And I also moved to a completely different topic because I joined a group of my colleague who is a material scientist. And what we have learned together, we are now trying to explore that. And we've explored that in a few directions. For example, to explain the point how a crystal develops charges. Because if you eat some crystals, you can create charges. How we can understand that phenomenon which is known for 2,000 years, right, on the molecular level. And for that reason, we are using the same tailor-made additives in crystals. No problem. That is no problem. And also the ice nucleation using the electric field, how to use and to explain the field of electric, how an electric field induces icing. Because water, ice crystals melt at 0 degrees, but water you can cool it down to minus 40 degrees without freezing. And this is a very important phenomenon. For example, if you want to have rain, you have to spread the silver iodide crystals in the atmosphere, and these silver iodide crystals are developing charges when you cool them. Okay, and people have not announced that. They didn't took into consideration the fact that they are charged, and this charge affects the ice nucleation. And I think that by using our amino acid crystals, tailor-made additive, all these crystals that we have developed during the years, and by using them, they are very useful to try to solve all these particular projects. This is important.
I want to ask you about, of course, a question that everybody, non-scientists, are interested in, and this is the origin of life. How close can we get? I mean, this is complete speculation. How close can we get, and how close did you get to the deciphering or to propose a potential pathway for the origin of life?
I think the origin of life is a very unique scientific question, because you cannot provide a real reply where life started and how it started. What you can do is you can design models. For example, in chirality, you say all the biological world is composed of molecules of one kind. Okay? You can, in the laboratory, you get the two of them. You can develop methodologies where you can generate only one of them. And you say, aha, this is a feasible process. But you don't know whether this method is the method that started the chirality, was responsible for the origin of chirality. You don't know whether it happened. It could happen in Mesopotamia, it could happen in Brazil, because if you look on the crystals of quartz, let's say they have one kind in Mesopotamia, they have another endedness in Brazil. So you don't know where this started. And you don't know whether it started by crystals. Maybe it started by some other techniques and by some other methods. So what people are doing, you can present all kinds of models in this field, okay? And you can speak about feasibility. This is feasible, but you don't know whether life started exactly in this particular way.
But if you understand the origin of chirality, you may understand the origin of life?
No, I don't understand that, but what I can say that this is one factor. And you can say this started in the beginning, or you can start it in the late stage of evolution. Because if you take the biological system, everything appears in chirality. They are much more complex, and maybe at certain stage, one generated a very complex left-handed system, which could propagate, like the DNA propagates, and then chirality is that in a very late stage. There are some others that claim that it started in the very beginning. There is another theory, they come from Mars. They're saying life started in Mars, and maybe some come to Earth. So this is I think this is very difficult. But the point that we ask in the field of origin of life is feasibility. Is this feasible, right? Is it feasible that you can in a laboratory perform a reaction which will give you one product and not will give you the other product?
Okay.
And that this is what I would say.
I was thinking that that was why I found the experiments that are doing now with the Mars rover, that they're looking for life, signs of how life had started, if it had, on Mars, because they are looking for magnetite, biogenic magnetite. If you can find magnetite crystals, which are, say, size of a microns, and those crystals are perfect, they can only be biogenically developed.
Okay.
And I think that was a fantastic idea.
Wow.
And I think that is related to the sort of experiments that they are doing now and that they've been trying to do on Mars. But I was wondering about something else. That is, for trying to study the atmosphere of all the exoplanets.
Wow.
We've now found about several hundred planets, all in the part of our galaxy, which resemble the planets of Earth and the stars and the suns. They could have, but if you could determine by setting up satellites, and you could try to measure spectroscopically whether there's oxygen and nitrogen and what kind of gases surround those planets, that would be one way of determining whether there is life on other planets. That was the one thing I think I would like to be involved in such experiments had I been young.
Wow.
And I think the point is that again, even if you show that you have chirality on Mars, okay?
Yeah.
This doesn't tell you that this is the way how chirality started on Earth.
But that could be but
This
it
is a
could be right-handed.
feasibility. Yeah, it could be right-handed.
But that's true. But even that is interesting.
Yeah.
Okay.
A lot of physics will tell you that the amino acids, let's say, have a preference for left-handed, but the amount of that is so small that it's very difficult to try to see that they are responsible for the. So that's maybe a difference from a stochastic model. I'm saying that maybe it's a stochastic process, and they want is a deterministic process. But even so, you ask how this has been created. So I think what is more important in this field is feasibility.
Okay.
You ask to say feasibility, and then you can say that maybe this factor has played a role, but you're not sure that this was really the reason for the creation of life.
I want to ask you two questions, one related to the past and one related to the future. Let's do an exercise about the past. If you had an opportunity to speak to Louis Pasteur, if he would come for a dinner, what would you ask him?
I have, okay, you start first and I will speak afterwards.
I think I would ask him the following. The two crystals that he investigated were investigated previously by the leading crystallographer at the time, Schulich. Investigated two crystals, and he published a paper which was published in the French Academy of Science. There is no any morphological difference between the two crystals. And then Pasteur, after the publication, decided to pick the two crystals and they find the difference. And I would ask him, how you find the difference? What you led to this? I mean, because you find this very small difference that one rotates left and one rotates right. What led you to make this particular discovery that after this important publication of the leading crystallographer of the time, of your time?
Well, if you look at Alexander Fleming, I mean, everybody knew what he saw, but he was the first one to ask why.
Yeah.
I think it was you have to look at the connection between the structure of the molecule and the structure of the crystal and the morphology of the crystal. Now, in the 19th century, there was a man called Bravais. He found the 14 space lattices of crystals. There are 14 ways it is monoclinic, orthorhombic, etc., etc. But he published that result in 1850. But that was 2 years after Louis Pasteur had published his work. And so even the knowledge, Pasteur didn't even have the knowledge of the number of different lattices crystals form. But was also more important was that it was only at the end of the 19th century that the 230 ways in which you can arrange molecules into crystals that work was done by a man called Fedorov, a Russian, and Schulich, a German. So Pasteur at that time did not know this. He was 26 years old, and this was 1848. But there's one possibility. If you have an orthorhombic crystal, that crystal, the contents, the molecules if the molecules are centrosymmetric, then the crystals will all have faces which are consistent with a centrosymmetric crystal structure. But if the molecules are chiral, then it could well be that several of the faces, which we call hemihedral faces, will give the crystal its chiral character. And so I would have asked Mr. Pasteur, Louis Pasteur, could he have made that connection between a molecule that is chiral and a molecule that is non-chiral and the faces of the crystal? This is something that is so deep and so fundamental. It was in a sense that question that we tried to address when we worked on that problem 150 years later.
Probably not, because this is before Van Hoff.
Yes,
and the idea of
yes.
chirality.
But the point was the following. I think there is a point there was a big discussion between physicists and chemists in this time. And the question whether there is the existence of molecules whatsoever.
Yeah, but Meir molecules, Dalton knew this.
No, but in his experiment, he confirmed that the world is composed from molecules.
Yes.
Actually, he answered that question, because the moment that he dissolved the crystal and he saw the rotation, right, and after that he crystallized the crystal, and then actually this was a very strong indication that you have molecules. You're dealing with molecules which are composing the crystal, which are not decomposed in water, and not decomposed in the solvent. They combine together and they give you the same crystal. The other question that I would ask him, how come that you left that field, which was so important, and you moved to other fields, like immunology, like how wine is made in the wineries, pasteurization of the milk, to beer, how you selected your projects.
Yes.
The problem. That's probably moving today, if you look on immunology, this is a field which is very different from the field of organic chemistry. And to take such important discovery and to leave it out, because after that Van Hoff and others came very shortly afterwards, and I think in his time, he could have really made some kind of progress in that particular field. But I think that's the genius, right? That can pick up different problems.
He had genius. I mean, the fact that he understood that there was a connection between the morphology and the molecular structure was amazing.
And this was done by the ability to force the crystal to crystallize in a given morphology. This was our, I think, the major problem.
Okay.
He got the morphologies and he separated them. In our case, by using this method that we have developed, we were able to take a crystal, for example, a simple crystal, any crystal which is benzamide, a crystal, we could get it in one type of needle, another type of needle.
Shape its morphology.
Thin part, we could really manipulate the morphology of the crystal, and by this ability to manipulate the morphology of the crystal, we were able to find the connection between the crystal and the chirality of the molecule.
Yeah.
Well, it's very likely that Pasteur himself didn't appreciate how revolutionary was his discovery.
That's also possible.
Yeah.
But he made the connection.
Okay.
No, I think this was because I think the major event was that he was able to show that materials are composed from molecules, which was very, very important. And the second part, of course, was very important, was the question of that the biological world is composed of molecules of one endedness, not of the two endedness. I think this was very, very important. But he made all kind of errors, because after that he wanted to prove that magnetism is responsible for that. And I think that only more recently, I think Ron Naaman demonstrated that maybe what they call spins can really, magnetic spins can really control chirality, which is the central process.
I want now to go to another hypothetical question, and that's going to be the last one. If we assume that we are now going 50 years back in time, and you are now starting your career as independent professor, maybe age 35 or so, what problems would you pick?
Okay, I can tell you that because when I retired 20 years ago,
Yeah.
I joined my colleague and I'm continuing to my work, and I have some young students. And I always used to discuss this question with my students.
Okay.
And I have quite clear opinion about it. So let us go back to the Pasteur that you mentioned before. This was 19th century, okay? So a single scientist could work in chemistry, immunology, origin of life, on very different topics.
Natural philosopher.
And philosopher.
Yeah.
And I think every particular topic today is a separate field, okay? So if you went to the 20th century, if you go to the 20th century, you can see that people becoming more and more specialists. They confine us completely with something which is much more specific, okay? And then you don't find scientists like Pasteur that could really make such breakthroughs in all these different fields which are so different from each other, okay? And I think that now moving to the 21st century, it becomes clear that the project that they have to use and to try to solve are much more complex than what was on the previous one. And it becomes clear today that if you want to work on a serious problem, you have to collaborate. You have to collaborate with other scientists, like what I'm doing today. I'm working with material scientists, and we work with theoreticians that know mathematics. It is quite clear that your future problems will be multidisciplinary, and you have to collaborate with other people. In order to collaborate with other people, you have to understand the language of the other people. You cannot be an expert in other people, in other fields, but you can, if you want to collaborate, you have to know their language. You have to understand their language. So what I can suggest you first, if you're in high school or in the university, to learn mathematics, chemistry, biology, physics, environmental sciences, geology, to be much open, okay? To try to understand the language of the others. And in your future life, when you're going to select an important problem, no matter whether it is physics or chemistry or mathematics, to work on that, to concentrate on that, but also to know to ask questions in the other subfields, to be able to collaborate with other people, and then to provide answers to your problem.
But what specific
I would
open
say,
questions that you want
well,
to...
there are many open questions that you have, let's say, in the atmospheric sciences. We don't understand the atmosphere. You cannot predict the atmosphere. You have all this, you have these hurricanes in the
Climate
world.
change.
Yeah, and then you want to control them. You don't know how to do that. You have many complicated problems in biology, how the mind works, how it operates, right? And you have many times in the material sciences. You would like to understand material science on the molecular level, okay? You want to understand the molecular level to be able to design new materials for energy. And you want to have new materials for in biology, in medicine, some problem. So you have to decide, you have to elect a kind of a multidisciplinary question, which is important. And in order to be able to solve such kind of problems, you will have to collaborate with other people, and therefore you have to learn all these particular different methods, not to concentrate only in, let's say, in chemistry or in physics, but to learn to be much more problem to be able to tackle this problem.
Oh, well, I thought of this problem many times, and I asked myself, how could I reach the jackpot? Right? How do you reach it? And I was thinking that it is related to the question of life in the outer universe. And for a long time, I thought this was impossible to get information. But all of a sudden, with the knowledge that you have, so many thousand planets in the outer universe, which are very much like that of Earth. And then I started thinking, my God, there must be a way in which we can determine whether there is some form of life, and that is by looking at the atmosphere. If I could build a satellite, space satellite, that would for years travel and that would collect information on the size of such potential Earths, on their suns, on all information, and even on the atmosphere surrounding such planets, maybe that would be the first step. And then there's Mars. Maybe if one could find, I think it is very interesting that the Americans have now landed these space, and to in fact look for life on such planets. I think that must be a wonderful, I think for me, that is hitting the jackpot. The problem is, of course, when you go all out on such a, it's like when Ada Yonat, what would have happened had Ada Yonat would not have succeeded? But I think that is it. If you chance, it is, I think, of course, what Meir says is very important. But I think that is, if you want to hit the jackpot, something really interesting, you have to try to do an experiment which is really outworldly. But this is my opinion, of course.
There's another point, I think, in this, to add to this, because the question is, can you constitute another satellite somewhere where life, let's say, if our world come to an end, and it will come to an end sometime, can you create new globes somewhere in the universe where we can continue the life that we have on Earth, right?
Yeah, colonize other planets.
Yeah,
yes, colonize
other places. Yes. There's a problem, which will survive more than the one from the Earth, right? Yeah. But my impression is, in general, I'm sure that there are many interesting projects. Yeah. And I think that you can find many interesting projects that you can solve. The time is ripe to try to solve these problems. Because there are certain points, the problems that Pasteur could not solve. We could not solve the structure of the structures of these molecules. He has to wait for
140 years
for the X-rays. He has to wait for the Braggs and for Röntgen and Braggs and for all these people. But I think that but the point is that you solve some problems and you create some problems which are much more complex by using the information, using the computers, right? Using all these instruments that we have today, NMR and all these tools that we have today with which we can really solve particular problems. The point is how you select the problem that can be solved in this time okay? And
Yeah.
I'm sure that this problem will be multidisciplinary. So your ability to try to collect, to interact with some other scientists and to try to provide a vision of some to this point.
Okay. I think we are sitting for quite some time here.
Yes.
I thank you very much. It was very interesting for me. We hope very much that we'll be able to do the World Prize ceremony in early June as planned. That the situation will allow us to do so, and I would like to congratulate you again very much.
I think that I would like to thank the Wolf Foundation because I feel that it's a very great privilege for us to do that, to get this recognition. We deeply appreciate it. I think that it was taken by surprise, complete surprise. We were not,
Complete.
not thinking for that, but I think that it is really, I think that the Wolf Prize is something which is so important and well recognized. This is recognized by colleagues abroad, not from colleagues from Israel. I think this is much more important.
Yeah, of course, particularly in chemistry, it's considered the second most important prize in the world after the Nobel, and obviously has a predictive value of something close to 40%. So take note of that.
But I think we were lucky that we worked at the Weizmann Institute, and that we were also given by so much support by the Weizmann, and that we had the opportunity to work with students and postdocs at with almost complete freedom. That was an enormous advantage.
And I think we have to thank also, I think in this occasion, our teachers.
Yes, our
and
teachers.
I would like to have a special thank to Gerhard Schmidt.
Yeah.
I think the fact that he, in the 50s, he constituted this multidisciplinary department. I think it was very different. If I remember the other departments, they were not multidisciplinary. No problem. And there is another point which we have in this institute. We have new reorganization. Actually, our department now is a new department. From February 1st, we have a new department of what they call is molecular chemistry and material sciences, which combine the organic chemistry department and the materials chemistry department, and also combine part of the structural biology with some of the structural chemistry or the chemistry. So during my stay at the Weizmann for so many years, I had three reorganizations. We started in the X-ray department, we moved to the chemistry department, we moved to the structural chemistry department, and then materials and interfacials, and now a new department. And I think that this has a big advantage because it forces you to stay, to meet other colleagues from completely different education and different interests. And I think this collaboration between, I think, is important, very important, also in detecting projects that can be solved, that you thought before that are not, you could not solve them.
In other words, Meir, the Faculty of Chemistry at the Weizmann Institute is the faculty that is the most diverse than any other faculty in this institute. That is the beauty of the Faculty of Chemistry.
And we have also to appreciate, I think, our collaboration with people abroad. For example, Leslie has collaborated with Jens Nilsson as a kind of person who did very important studies, pioneering studies in the field of scattering from surfaces. Okay, and we had the opportunity to interact with many colleagues from Yale, like McBride, from New York State, like Michael Ward and Bart Carr, with Japanese, like Kenzo Soai, with Spanish people, like Weizmann and others. I think that these interactions, international interaction, not only, I think are very important to the progress of science in general.
Well, you mentioned Gerhard Schmidt, and I should mention also one thing which he's responsible for, and that's the establishment of the nucleation of the relationship, diplomatic relationship
Yeah.
between Israel and Germany. Talking about crystals, he was the seed. He started the
No,
nucleation.
established an X-ray laboratory in Heidelberg.
Yeah.
That's the problem.
Yes, I did the dirty work.
Okay.
Okay.
So I think.
Thank you very much.
Okay.
I think it
Thank
was very interesting.
Thank you.
The problem,
Yes,
and again,
yeah.
thank you for the
It's a
for the
pleasure.
prize. I think thank you for the prize. We are really we're so excited about receiving this recognition. I think it's very important.
Okay.
I think
happy.
I'm lucky to be alive.
That's right. This is what I wanted to say. Exactly.
You're lucky to be
You have
alive.
to come to the age of 80 in order to be able to
Yes,
to get the
lucky to
recognition.
be alive.
So young people who die early, they have a problem.
Yeah, Gerhard Schmidt. Yeah.
Yes, Gerhard Schmidt.
Like Schmidt.
Yeah.
That's right.
Yeah.
I remember.
Okay.
The point is that when you make some new discoveries, it takes time until this discovery is recognized.
Yeah.
Because
Yeah,
if
at
it becomes
least-
something which is different
Yeah.
and not acceptable by the community, and you come with a different idea, I think that's it. Leslie gave a lecture in Bergenstock. You know Bergenstock,
Yeah, of
right?
course.
He gave a lecture about this, and they thought that this was a joke lecture.
Yes, in 1982, they actually thought, well, at each Bergenstock lecture meeting, there was a joke lecture.
After dinner speech.
Yeah.
No, yes, like an after dinner. It was a joke, you give a lecture and it is full of bluff. And they honestly, many of them thought that I was giving the joke lecture.
Amazing.
Yeah, I remember when I was in Bergenstock, it was H.C. Brown. So he gave a lecture about whistling molecules, molecules which can whistle. You know? That's the problem. And people in the beginning start believing that because he made it in such a very intellectual way. He was showing infrared, showing this kind of absorption. The molecules start whistling.
So at the same time.
The joke lecture.
Okay.
Joke lecture in this.
Okay. So thank you very much.
As I said, thank you for the prize that we are, and also for this interview, which we enjoy. I enjoyed very much.
Yes, it was a pleasure to have received notice of something of which we knew nothing about. And we are deeply grateful for what has been done. Yeah,
Okay.
no doubt about it.
Okay.